All right, so hi everybody, welcome back. What we're going to be doing today is continuing our lecture on heat and the first law of thermodynamics. And this is what's covered in chapter 19 of the textbook. By the end of this video, we'll be completely finished with the content from chapter 19 that I wanted to cover. And where we left off last time is we were talking about four really important ideal gas processes. So one of them was called isochoric, where we hold the volume constant. Another one was called isobaric, where we hold the pressure constant. And then we had isothermal, where we hold the temperature constant. And then there was this fourth one called adiabatic, which we haven't covered yet. We've covered the other three, but we haven't talked about an adiabatic process yet. And that's going to take a little bit more time to build up to. So first, we have to take a little bit of a detour and talk about something called equipartition of energy. Okay, so the first thing I want to do here is kind of set the stage. So I want to motivate why this idea called equipartition of energy was developed, where it comes from, and sort of why we should believe it's true. Because if I just show it to you without any context, it may seem a little bit strange. So let's kind of build up to it. So here's what we have so far. We talked about molar specific heats, and in particular for monatomic gases, that means gases that consist of single atoms. The molar specific heat for a constant volume process, that's CV, we found that that was equal to 3/2 times R. We also found that CP, that's the molar specific heat for a constant pressure process, is CV plus R. Okay, so R is just the ideal gas constant, so we can plug that straight into these formulas. And so if we do it for CV, we have 3/2 times 8.314 joules per Kelvin mole, which works out to 12.5 joules per Kelvin mole. For CP, we're plugging in 3/2 times R for CV, and we're adding R to that, which gives us 5/2 R. And if you plug in the ideal gas constant and crunch the numbers, what you'll get is about 20.8 joules per Kelvin mole. Okay, so it's really worth sort of mentioning and repeating that these numbers that we just calculated are purely theoretical. Okay, so we started with the kinetic theory of gases. We did a whole bunch of derivations in the last couple lectures, and those led us to these calculations we just did, okay? But the amazing thing is you can compare these numbers to experiments, right? You can measure specific heats in a laboratory, and the table at the bottom of the slide shows you some of those measurements, okay? So let's go for helium. Let's take a look at helium. So if you measure the specific heat at constant volume, you'll find it's 12.5 joules per Kelvin mole. And if you do the same thing at constant pressure, you'll get about 20.8. Neon, same set of measurements. Argon, same two measurements. And then krypton, same two measurements. So the first four in the table, what they all have in common is that they're monatomic gases. These are just single atoms that fly around in the gas. Okay, so they all have the same specific heats, and they really agree with what we calculated. If we work our way down the table, now we're getting to molecules and more complex molecules as we go down the table. We can start with hydrogen. H2 is the molecule we're talking about here. So this is what we would call a diatomic gas, and that just means we have two atoms in the molecule, right? Two hydrogen atoms. And then same for nitrogen. This is another diatomic gas. Oxygen, O2, another diatomic gas. And if you compare all of those, you'll see the value of CV is different from the monatomic gases, but they're all the same for the diatomic gases. So they're all around 21 for CV, and they're all pretty close to 29 for CP. So there's something interesting going on here. Okay, all of the monatomic gases have the same specific heats, and then apparently all the diatomic gases have the same specific heats. So we want to understand why that is. Why is it that the specific heats for these gases seems to depend on the number of atoms in the molecules. So let's try to figure out what's going on here. Okay, so what we saw in the table on the previous page is that the experiments are showing that molar specific heats, CV and CP, they depend on what we call degrees of freedom. So a degree of freedom is just a way that a molecule can have energy. And when we count up all the degrees of freedom, we're just counting the number of independent ways that a molecule can have energy. So we use the variable lowercase f for degrees of freedom. And that may seem a bit abstract, so it's a lot easier to grasp the idea if we just look at some examples. Okay, so we'll start with a monatomic gas. Think of something like helium or argon, just a gas that consists of single atoms. And so what we should be thinking in terms of how this atom is moving around is it's a point mass that has some velocity, and it's moving in three-dimensional space. So there's an x, y, and a z component to the motion that we have to keep track of. So I'm going to start by reminding you that if we know the x, y, and the z velocity, we can calculate the speed. It's basically the Pythagorean theorem. So the speed, v, is the square root of vx squared plus vy squared plus vz squared. That's how we calculate speed. And if I want to know the energy that this atom has, well, it's fairly straightforward because the only type of energy it has is kinetic energy. The only thing the atom is doing is it's translating. It only has translational motion. It's just moving from point A to point B. That's all it's doing. So therefore, the only type of energy it has is kinetic energy, 1/2 mv squared. And we just saw that we can think about v as the square root of vx squared plus vy squared plus vz squared. So if you square that, you're just getting rid of the square root that we had over here. So in other words, the energy is 1/2 m vx squared plus vy squared plus vz squared. And if we expand that out, just multiply 1/2 m by each one of those terms in the parentheses, we have 1/2 m vx squared plus 1/2 m vy squared plus 1/2 m vz squared. Okay, so that's as much as you can expand this formula out, okay? So what we say is there are three independent ways this particular type of gas can have energy, right? It can have motion in the x direction given by this term, motion in the y direction given by this term, and then motion in the z direction given by that term. So when we count up all the independent ways the molecule can have energy, there are three. So what we say is F is equal to 3 for a monatomic gas. Okay, so hopefully you have a better sense as to what the degrees of freedom mean when you see this example. Okay, so the next example to look at is a diatomic gas. So think about molecules of gas that have two atoms connected by some kind of chemical bond. So you can think of things like O2, which consists of two oxygen atoms, or N2, which has two nitrogen atoms, or CO, carbon monoxide. It's a carbon atom plus an oxygen atom. So those are the sorts of things we're thinking about here. And it helps to have a picture in your mind about what a diatomic gas molecule looks like. So for our purposes, you can think of it as a mass over here and then another mass over here. And they're connected to each other. There's not literally a little rod in between them like this, but this represents the chemical bond in between the two. So the center of mass of the molecule is located, somewhere along that line, so we'll label that as Cm. So one way that the molecule can have energy is it can translate, it can move around in 3D space. So what we mean by the molecule is translating is we mean the center of mass is moving around. It has some velocity. So the velocity, we'll label that as v. Okay, in addition to that, the molecule can rotate. So even if the center of mass itself is not moving, it's just staying stationary, what can happen is the molecule can rotate around its own center of mass. And there are two ways it can do that. So first, we can imagine it rotates around this axis right here. And so what that would look like is it's spinning this way. Also, we can imagine it's rotating around this axis right here, which would look like spinning this way. So those are the two types of rotations that the molecule can have. And in addition to that, the molecule can vibrate. So the two atoms in the molecule, they don't have to just be some fixed distance apart. Instead, what can happen is they can get closer together and then get further apart and then closer together and then further apart, vibrating back and forth. Okay? So what you should be picturing when it comes to the vibration is you have two little masses and they're connected by a spring. So again, it's not like there's literally a spring in between them, but the force between the two atoms behaves a lot like a spring. So a spring is a good model of what's going on in terms of the force between these two atoms. Okay, so those are all the different ways the molecule can have energy. So now we want to write down a formula for what that energy looks like and all the different parts of it. So first, we're going to have the same expression we had before for a monatomic gas, which is 1/2 mvx squared plus 1/2 mvy squared plus 1/2 mvz squared, because the molecule can translate in 3D space. So there are 3 degrees of freedom for the translational motion of the center of mass. Okay, but we also are going to have 2 terms for the energy of the rotations. Okay, so if you remember from Physics 45, the rotational energy of a spinning object is given by 1/2 I omega squared. Okay, so I represents the moment of inertia, omega represents the angular velocity. I think this is the only time in this class we're going to actually see this equation and use it, but we need to write it down so we can account for the energy. So we have 2 of these terms because, again, we can rotate around 2 different axes. So that's what this and this term represent. And in total, we have 2 rotational degrees of freedom. Okay, now let's move on to the vibrational degrees of freedom. And here's how you should think about that. So when it comes to the vibrations of the molecules, there's kinetic energy associated with that because the atoms can move back and forth, and that motion has to be accounted for. There's kinetic energy. So there's a 1/2 mv squared term to account for that. But in addition, there's a 1/2 kx squared term, which represents the potential energy stored in the spring. Okay? So therefore, we have 2 vibrational degrees of freedom. And if you try to add all of that up, we have 3 plus 2 plus 2. So in total, we have 7 possible degrees of freedom for a diatomic gas molecule. Okay? So those are the 2 cases you need to know. You should know how to count the degrees of freedom for a monatomic gas, which comes out to 3. And then for a diatomic gas, you should know how to count the degrees of freedom we just went over, which in total comes out to 7, but it's a little bit more complicated than that, and we're going to get into that just in a second. Okay, so now we're ready to get to the equipartition of energy. So here's what the equipartition theorem actually says. So when we have a system in equilibrium, its internal energy is shared equally among all of its active degrees of freedom. On average, each degree of freedom contributes 1/2 kT to the internal energy, where K is Boltzmann's constant and T is the temperature. That's what that means. Okay, so to explain that in a little bit more detail, when we talk about internal energy, remember this means the energy that the molecules themselves have because of their random motions. And then when we talk about degrees of freedom, we're just talking about the different ways that the molecules can have energy. So what this is saying is there's no degree of freedom that's favored. Okay, they all share the energy equally. So it's not like a vibrational degree of freedom has more energy than a translational degree of freedom. It's just shared equally. There's nothing that's favored over another. Okay, so with that in mind, we can now come up with a new formula for the internal energy of some kind of system with a lot of different molecules. So let's break this down term by term. On the left side, we have the total internal energy of all of the molecules. And the way you want to think about this is we're going to start by multiplying by n, where n is the total number of molecules we have. And the rest of the expression over here just represents the energy that each molecule has. So think of this as saying it's the number of molecules we have times the average energy that each molecule has. If we do that multiplication, we'll get the total energy that all of the molecules have. Okay, so F is the number of active degrees of freedom per molecule. So that's the number F we were referring to earlier. And then 1/2 kT is what, on average, each one of those degrees of freedom gets in terms of energy. So this is what the Equipartition theorem is telling us, is to put 1/2 kT at the end of that expression. Okay, so based on what we just saw, we're going to derive some more general expressions for molar specific heats. So I want to remind you that up until this point, we derived formulas for CV and CP, but they only worked for monatomic gases. Now that we have the Equipartition theorem, we can derive more general formulas for these specific heats that don't just apply to monatomic gases. So let's see how to derive those formulas. Okay, so a couple derivations here. What we just found from the Equipartition theorem is that the total internal energy of some kind of system with a bunch of molecules is N times F times 1/2 kT squared. So that's Boltzmann's constant. So in other words, just to write this in a slightly nicer way, let's say F over 2 N kT. Okay, well, remember from the ideal gas law that PV can be written as NKT, but equivalently, we can write this as nRT. So in other words, capital N times KT is the same as lowercase n times RT. So I can write the internal energy as F over 2 times lowercase n RT like this. And we previously derived in the last lecture that delta E internal for any process whatsoever is equal to N CV times delta T. So in other words, we have these two different expressions for internal energy that we derived kind of going from two different approaches, and we can set them equal to each other. So set delta E internal expressions equal. Okay, so the first one we have is F over 2 N times R times delta T. That's what we got from the Equipartition theorem. And then we have N CV times delta T, which we derived in the last lecture. Okay, so cancel out N as well as delta T. And what we have is CV is equal to F over 2 times R. And remember, for a monatomic gas, we have F is equal to 3, right? So if you plug in F equals 3, we get 3/2 R, which is the formula we had before. But this also allows you to deal with things that aren't monatomic gases that have different values of F. So we also previously derived that Cp is equal to Cv plus R. So if we plug in F over 2 times R for Cv, and then we add R to that, we're going to get F over 2 plus 1 times R. Okay, so these two expressions here, I'll put a box around each one, are the general formulas for the molar specific heats of gases. Okay, and that proves the results that we were trying to show, which is that for a constant volume process, our molar specific heat, Cv, is going to be F over 2 times R. If we have a constant pressure process, Cp is equal to F over 2 plus 1 times R. And all we need to know in order to calculate a specific heat this way is the number of active degrees of freedom per molecule. Okay, and that's something I showed you how to do for a monatomic gas and a diatomic gas. You know how to count those degrees of freedom. We also need to know R, which is the ideal gas constant. Again, that's 8.314 joules per Kelvin mole. So as long as you know those two things, you can calculate any specific heat. But there's a slight complication to what I just said, okay? So when we talk about F, the number of degrees of freedom, we're actually talking about the number of active degrees of freedom. So what I mean by that is it's possible for certain degrees of freedom to be frozen out, meaning they're not really contributing to the energy if the temperature is too low. So let me show you a graph of some experimental data where we have a diatomic gas, okay? And on the vertical axis, we're plotting out Cv. So you can measure the specific heat of the gas, and that's what's being plotted out here. And temperature is being plotted on the horizontal axis. Okay, so basically we're saying, how does the specific heat change as the temperature changes? Okay? So at very, very low temperatures over here, just a couple of Kelvin, just barely above absolute zero, if you measure the specific heat of a diatomic gas, you're actually going to find it comes out to 3/2 R. And that means F, the number of degrees of freedom, is 3. Okay, so what is that telling you? Well, what that's telling you is we have 3 translational degrees of freedom. Those are still there, but the vibrational and the rotational degrees of freedom are somehow not there when the temperature is low. And what we say is they're frozen out when the temperature is low. Okay, as you increase the temperature, the specific heat will stay at 3/2 R for a while, but then it'll start to rise, and then it will level off again at about 5/2 R. So what does it mean to say that the specific heat is now 5/2 R? Well, that means F is equal to 5. There are now 5 active degrees of freedom. Okay, so now you have those 3 translational degrees of freedom, as well as the rotational ones, but the vibrational degrees of freedom are frozen out. Those aren't kicking in yet because the temperature is too low. So as we continue on, okay, and increase the temperature even more, then the specific heat will rise again, and it will level off around 7/2 R. So now all of those degrees of freedom, all 7 of them for a diatomic gas, are actually active. And it takes a really high temperature, as you can see, like a couple thousand Kelvin typically, for all of those degrees of freedom to be active. Okay, so all I'm showing you here is just some sort of experimental data. It's just the fact that at low temperatures, you freeze out vibrational and rotational degrees of freedom. At kind of medium temperatures, you freeze out the vibrational degrees of freedom. And then it takes really, really high temperatures until all of those degrees of freedom become active, okay? So I am going to explain a little bit as to why that is, but the basic idea is this. We say a degree of freedom is going to be frozen, it's not going to be active, if the minimum energy for that degree of freedom is much greater than 1/2 kT. So let's get into that in a little more detail. Okay, so let's try to answer the question, why are certain degrees of freedom frozen out? So we know that some degrees of freedom can be frozen out, meaning they just don't count when the temperature is too low. So let's try to understand that. So in order to understand this fact, we do need to bring in quantum mechanics, because quantum mechanics is the framework in physics that we really need to use if we want to study atoms and molecules and things going on at that really tiny scale. So we're not going to dive too deep into this, but let's just write down a fact. In quantum mechanics, okay, vibrational and rotational energies are discrete, not continuous. Okay, so what I mean by that is, let's take the example of a rotation. Okay, so this is our molecule, a diatomic molecule. It's kind of shaped like a dumbbell. And we can picture it rotating like this, okay? And so there is some energy associated with that rotation. And at the bottom of this scale, we'll put 0, which represents no rotation at all. So you might be thinking, well, the energy of that rotation can be just anything. It can be anything you want. But quantum mechanics says that that's not true. In fact, the energies are discrete, so it can only take on certain discrete values. So for example, you can have some energy over here, E1. That's the lowest possible energy. You can have some energy after that. Let's say it's E2. It's the next possible energy. And then E3 and so on. But you're not allowed to have energy in between those ones that I pointed out. Okay, that's what it means for energy to be discrete. It can only take on certain values. Okay? But remember that the equipartition theorem says that each degree of freedom gets 1/2 kT worth of energy. But what happens then if the lowest possible energy for the rotation is much, much bigger than 1/2 kT? In other words, like what if 1/2 kT is down there somewhere? Well, then the molecule doesn't even have enough energy to rotate in the first place. So what we say is that degree of freedom would be frozen out if this lowest possible energy is a lot more than 1/2 kT. So when we turn the temperature up and T increases, then we can have that degree of freedom be active, like if we're over here. So here, we're frozen out down here, clearly, right? But if, 1/2 kT were up here somewhere, that just means the temperature is higher. We would say it's active. Okay, so that's why certain degrees of freedom can be frozen out when the temperature is low. Okay, so the next thing we're going to do is take a look at the molar specific heats of solid materials. So we can actually take what we learned, the equipartition theorem, and everything that we derived from that, and apply it to a solid material. Okay, and we don't have to just restrict ourselves to ideal gases. So when we think about a solid material, what you should be picturing is a lattice with a bunch of different atoms spaced apart by fixed distances. And the lattice is three-dimensional. Okay? There are going to be forces between the different atoms in the lattice, and we can model those forces by thinking of a little spring in between the atoms. So again, this is not literally what's happening, but the forces between atoms are very similar to the forces you would get if there were a little spring in between them. So we kind of model it that way so it's easier to think about. Okay, so what we need to do if we want to know specific heat is count the degrees of freedom. Okay, so in other words, what are the different ways that an atom in this lattice can move around? Well, it can't translate. It's pretty much stuck right here. It's not going to be moving a huge distance and end up somewhere very far away. There's no translation to think about. There's no rotation to think about either. All that's happening to these atoms in a lattice is they're vibrating. So that's all that gets to happen is you have vibration. And we have vibration along the x-axis, so we can imagine the molecule vibrating this way. We can also have vibration along the y-axis and along the z-axis, okay? And remember that for each one of those, we have 2 degrees of freedom for vibration. Okay, so we have 2 degrees of freedom for vibration on the x-axis, 2 for vibration on the y-axis, and then 2 for vibration on the z-axis. That's a total of 6 degrees of freedom that would be possible. But remember, they're not necessarily all going to be active. So 6 is just the maximum possible. Okay, so actually I forgot to put this on the slide, so I'll write it over here. CV is equal to F over 2 times R, right? That's what we derived using the equipartition theorem. So if we're saying F is equal to 6, then we're going to have 6 over 2 times R, which is just 3 times R. And we can calculate what 3 times R is. It's 3 times, so it's 3 times 8.314 joules per Kelvin mole, which if you do that calculation gives you 24.9 joules per Kelvin mole. So this is what we're predicting. For a solid material, as long as the temperature is high enough so that all the degrees of freedom are active, the specific heat you should expect is 24.9 joules per Kelvin mole, and it shouldn't depend on what the material is. Well, let's look at some experimental data. So the graph that you see on the bottom right of the slide is we're plotting specific heat, CV, over here, and temperature over here. Okay, and then the different curves just correspond to different materials. So the first one is lead. So lead, the specific heat starts off very low, but it shoots way up as we increase the temperature, and then it levels off right around 25. Okay, so in other words, once all the degrees of freedom are active for lead, the specific heat is 25 joules per Kelvin mole. Okay, this one is for aluminum. Again, it starts off low because a lot of degrees of freedom are frozen out, but once the temperature is high enough, it levels off around 25. Same for silicon, same for diamond. And they're kind of different in terms of like how much do you have to heat them up before all of those degrees of freedom become active. But the point is, once they're all active, they all have this same specific heat that we calculated over here. Okay, so that's everything we wanted to say about equipartition. So the important takeaways are you can calculate specific heats if we count degrees of freedom. And then also just remember that sometimes degrees of freedom can be frozen out. So you shouldn't be counting the ones that are frozen out. So how do you know whether or not a degree of freedom is frozen out? Well, the short answer is I'm just going to tell you. Okay, I'm just going to say in this problem, assume these degrees of freedom are frozen out and assume these ones are active. Okay, so with a statement like that, you should be able to solve any problem that I give you. Okay, so we needed to do all of that in order to get to adiabatic expansion and contraction of an ideal gas. So let's get into this. So remember, we have 4 types of ideal gas process that we need to know. We have keeping the volume the same, we have keeping the temperature the same, and we have keeping the pressure the same. And then we had this 4th one called an adiabatic process. And the definition of an adiabatic process is that there's no heat flowing into or out of the system during the process. So what characterizes an adiabatic process is that Q is equal to 0. So you're imagining the gas is expanding or it's contracting in some way, but the whole time there's no heat flowing in or out of the gas. Q is equal to 0. Now, it is a little bit of an idealization to say we have an adiabatic process because in reality, there's always going to be some amount of heat flowing in or out of a gas, no matter how hard you try to insulate it. But we can imagine that the system is so well insulated, your gas is so well insulated from the environment, that the heat flowing in or out is negligible. It's small enough that you can ignore it. Another way you could get Q equal to 0 is that you could just make the process happen so fast that there's not enough time for heat to flow or not enough time for any significant amount of heat to flow. So those are sort of the 2 ways you can have an adiabatic process. Again, just either have it very well insulated or have the process happen so fast that there's not enough time for heat to really flow. Okay, we're going to focus on the first one, just having a very well insulated system, because the second one, where it happens really fast, is automatically not something we're going to look at because it's not quasi-static. We only think about processes that happen very slowly, if you remember. Okay, so the picture you should have in your mind is you have the gas in a cylinder, something like that, and there's some insulation around the gas. So there's a material around it that provides a lot of insulation and it doesn't allow heat to flow through it. Okay? And so if we want the gas to expand, we can take a little bit of mass off of the piston, and then that will cause the piston to go up and it'll expand. And then if we want to contract the gas, we can put some mass onto it, and that will cause the piston to go down and contract. That's the picture of an adiabatic process. So again, this is all happening with no heat flow. Okay. Now to do some derivations. There are a bunch of relationships that we're going to derive for an adiabatic process. And basically, these tell you how pressure, volume, and temperature are all going to change during an adiabatic process. So let's derive these, and then we'll go through what they mean. Okay, so we're going to start by writing down the first law of thermodynamics for an ideal gas, which says Q is equal to W plus delta E internal. Well, the thing is, automatically, we know Q is equal to 0 because we have an adiabatic process. That's just what an adiabatic process is. It means Q is equal to 0. So in the first law, we'll have 0 on the left side. And on the right side, I'm going to write this in a slightly different way. Okay? I'm going to write the equation in what we call differential form. So for work, I'm going to write dW. So it just means a tiny infinitesimal amount of work. And for internal energy change, I'm going to write that as dE internal. Again, just think a tiny infinitesimal bit of internal energy change. Okay. So what do we know about work? Well, work is given by integral P dV. And the way you can think about that is we're integrating, little tiny bits of work, little infinitesimal bits of work to get the total. So each little infinitesimal bit, dW, is P dV. Okay, so in other words, you take the pressure times a tiny little change in volume, dV, and you get a tiny little bit of work being done by the gas. That's dW. That's what's going to go into our first law equation. What do we know about internal energy? Well, we know that delta E internal is equal to NCV delta T. That's a general expression we have. So if I'm talking about a tiny little change, an infinitesimal change in internal energy, the way I would write that is just NCV dt. Okay, so that's just the calculus notation for infinitesimal changes. All right, so going back to the first law equation, now we have 0 is equal to P dV, that's the work, and then we have NCV dt for the internal energy change. Okay, I'm going to make some substitutions into that equation by thinking about the ideal gas law. So PV is equal to nRT. And we can rearrange that to say T is equal to PV divided by nR. And what I'm trying to do here, guys, is come up with an expression for this, for dt. So this is kind of a problem, though, because pressure and volume are not necessarily constant. So I can't do what we did before where I just say, well, pressure is a constant, I'll pull it out to the front, or volume is a constant, I'll pull it out to the front. Instead, both of those things might be changing, okay? So if I want to find dt, little change in temperature, I have to use the product rule because I have the product of pressure and volume, P times V. If I want to know what dt is, I need to use the product rule. So the constant out front is 1 divided by nR. And here, let me just write, we're using the product rule. And so, okay, how do I take the derivative of P times V? How do I do that? Well, first, I just have P, and I leave that alone. And then I'll write dV next to that. And then I have to add that to V, leave that alone, and then dP next to that, right? This is how we use the product rule to get dt. Cool, so now let's take the first law equation that we wrote down over here and plug in what we just found. So we have 0 is equal to P dV plus, then we have NCV, and then what we're plugging in here is 1 over nR, P dV plus VdP. Okay, that's what we get when we plug in what we just found for dt. Okay, cancel out the ends, those go away. So to simplify what we have 0 equals P dV, and then we have plus CV divided by R, P dV, and then we have plus CV divided by R again, and then V dP. All right, so let's multiply on both sides by R, okay? So get rid of the R in the denominator, in other words. So we're gonna have 0 is equal to, so multiply all that by R on each side. So we have two terms here and here with P times dV in it. After we multiply by R, the first term is gonna have a factor of R in front of it. And the second term is gonna have a factor of CV because we canceled out the R on the bottom. And that multiplies P dV. Okay. We also have a single term that has V times dP in front of it. And the constant out front will be CV because, again, we canceled out the R on the bottom. Okay, cool. The next thing I'm going to do is remind you that Cp, the constant pressure specific heat, is CV plus R. In other words, that's what we have right here in the parentheses. So I can simplify this by saying we have 0 is equal to Cp times P dV plus CV times V dP. All right? Now let me explain what I'm going to do next. I want to divide on both sides by the following: CV times P times V. So the specific heat for constant volume times pressure times volume. Divide on both sides by that. Well, on the left side we have 0, so that stays 0. But then our first term becomes Cp divided by Cv. We get rid of the pressure term because we divided that out. We have dV on top, and then we divide out volume, so that's now on the bottom. Okay. Since we divided out Cv in the second term, that's gone. We have pressure, or we have dP on top. We divided out the volume, so that's gone. And we divide out pressure, so pressure is on the bottom now. So the next thing we'll do is we're going to define a new constant. Because it turns out when we deal with adiabatic processes, this ratio of Cp divided by Cv that you see in the equation, it comes up all the time. So we just give that a new name. We call that gamma. Okay, so by definition, gamma is the ratio of those two specific heats for constant pressure and constant volume. Okay, so we'll say 0 is then equal to gamma dV over V plus dP over P. So what can I actually do with this? Well, I can integrate both sides of the equation. So integrate both sides. And the nice thing about integrating 0 is no matter how many times you add 0 to itself, you still get 0. And on the other side, we're actually going to have two separate integrals. One is a volume integral, and the other is a pressure. Okay, so here, the first term is the volume one, which is gamma. And then we have the integral of dV over V, going from some kind of initial to some kind of final volume. And then we have a pressure integral, so we'll go from initial to final pressure. And again, dP over P. Okay, at this point, we should recognize what these integrate to. It's a natural log. Okay, when you have 1 over V, that integrates to the natural log of V. So I'm going to have gamma, and then natural log V, but I have to evaluate that from initial to final. And then I've got natural log P, but I have to evaluate from initial to final. So overall, here's what we're going to have. 0 is equal to gamma. I'll have natural log V final minus natural log V initial. That's how we evaluate that at the limits. And then I'm going to have plus natural log P final minus natural log P initial when I evaluate the second one at the limits. Okay, so I hope you remember some of the properties of natural logs because we're going to use them. The first thing we can do is remember that when I'm subtracting two different natural logs, I can bring those together as a single natural log by dividing. So in other words, the first term is gamma times natural log V final over V initial. And the second term is natural log P final over P initial. All right, so another thing we can do with that, if we just focus on the first term, whenever you have a constant out front of the natural log, you can actually bring it inside as a power. That's another property of natural logs. So in other words, we have 0 equals natural log V final to the gamma power now over V initial to the same power gamma. And then plus natural log P final over P initial. So lastly, we can now combine these two natural logs because we're adding them together. And the way that works is we have 0 equals natural log. Now I have to multiply those two if we're bringing them inside the same natural log. So I have P final, V final to the gamma over P initial, V initial to the gamma power. Okay, so we're almost there. The next thing I'm going to do, I want to get rid of that natural log now. The way I'm going to do that is by exponentiating both sides. So on the left side, I'm going to have e to the 0 power. And on the right side, I'm going to have e to the natural log of all of that. Well, e to the 0 power is just 1. So what we're saying is 1 is equal to P final, V final to the gamma over P initial, V initial to the gamma, or rearrange that to say P initial, V initial to the gamma is equal to P final, V final to the gamma power. Another way of saying that, by the way, is just that P times V to the gamma power is a constant throughout an adiabatic process. So it's constant for, I should say, an adiabatic process. So the product of pressure and V to the gamma power is something that stays the same. It's really important to remember. Then the last thing we'll do over here, and I'm kind of getting cluttered, so let's carve out a little bit of space over here. There's another way to write down gamma, okay? So gamma is the constant pressure specific heat divided by the constant volume specific heat. But we'll remember that constant pressure is CV plus R. That's one way we can write it. So I'm dividing that by CV. That's the definition of gamma. In other words, it's just 1, because CV divided by CV is 1, plus R over CV. And then we'll remember that CV is just, F divided by 2 times R. So the R's will cancel. And then we'll get 1 plus 2 divided by F. So gamma, in other words, can be written as 1 plus 2 divided by F. It only depends on the number of degrees of freedom. It only depends on F. Okay, so those are the results that we wanted to prove. Okay, so what we've established is that we have some relationships for adiabatic processes. So the one we derived is PV to the gamma power is constant. And another way of saying that is that if you take any 2 points along the adiabatic process called initial and final, then we can equate them. We can say P initial times V initial to the gamma is equal to P final times V final to the gamma. So that's how you can think about the expression. Now, there are actually 2 more. These last 2 relationships here, they're actually derived starting with the first one that we went through, and then using the ideal gas law to substitute out variables. So I don't want to go through that. It's just a bunch of algebra. But basically, you start with this one, and then you use the ideal gas law to substitute out the other variables, and you'll get these 2 relationships. So this says that temperature times volume to the gamma minus 1 is constant during an adiabatic process. And the last one says that pressure to the 1 minus gamma times temperature to the gamma is constant during an adiabatic process. So depending on the variables you're given, you might choose any one of these 3 to solve the problem. Now, the power gamma, as we showed, is defined to be Cp divided by Cv, but we can also write that as 1 plus 2 divided by F. Okay, so it's a lot of information, but these are equations that we'll use for adiabatic processes. And before we move on, let's just get some practice using those equations. So the first example we'll do is we have a diatomic ideal gas that expands adiabatically. Its volume doubles during the expansion. By what factor does its pressure change? We'll assume that the vibrational degrees of freedom are frozen out, but the rotational degrees of freedom are active. So let's work the first one out. Okay, so that first example, example 1, what we're going to use is the first relationship, PV to the gamma, is constant because we're trying to relate pressure and volume in this one. So right off the bat, we're going to need to know what gamma is. What power am I raising volume to in this relationship? And remember, gamma depends on F. So we have a diatomic gas, and we know that potentially we could have up to 7 degrees of freedom, but specifically we're told that the vibrational degrees of freedom are frozen out. So that means if we count it up, we have 3 translational degrees of freedom, and we have 2 rotational, but again, we're not including vibrational because those are frozen out. So we have a total of 5. Okay, so then gamma is therefore 1 plus 2 divided by F, which is 1 plus 2 divided by 5. So 1 is 5 over 5. We're adding that to 2 over 5, so 7 over 5. That would be our power. So the way I'm going to write this is P initial, V initial to the gamma is equal to P final, V final to the gamma. And what we're solving for here is the final pressure. P final, if we solve for it, is P initial times V initial to the gamma divided by V final to the gamma. So in other words, it's going to be P initial times V initial over V final to the power of 7/5. Okay. And what we're told is that the volume doubles. Okay, so if the volume doubles, that means the ratio is 1 over 2. In other words, the final volume on the bottom is 2 times the initial volume on the top. And we're taking that to the 7/5 power. So type into your calculator a half raised to the 7/5 power, and what you'll get is 0.379. So in other words, P final is 0.379 times P initial. So it's like 37.9% of the initial pressure. All right, so in that first example, we used the adiabatic relationship PV to the gamma is constant during a process that's adiabatic. And we found that P final is 0.379 P initial. So that's telling us by what factor the pressure changed. So we'll do another example, which is we have a monatomic gas that contracts adiabatically. Its absolute temperature doubles during the contraction. By what factor does its volume change? That's the question. Okay, let's work this out. All right, so to do the second example, we're dealing with a monatomic gas. So F is equal to 3, always for a monatomic gas, because we basically just have the 3 translational degrees of freedom. And nothing else. And the translational degrees of freedom can't be frozen out, so it's always F equals 3 for monatomic. So gamma, as we saw earlier, is 1 plus 2 divided by F. But what I want now is a relationship between temperature and volume, okay? Because this problem is posed in terms of temperature and volume. So we should be using TV to the gamma minus 1 is constant. That's what we should be using. So the power is gamma minus 1. Well, gamma minus 1 is 2 divided by F. And in other words, that's 2 divided by 3 for a monatomic gas. Okay. So what we're dealing with then is T initial, V initial to the power 2/3, that's gamma minus 1, is equal to T final, V final to that same power 2/3. So rearrange that because what we want is something about the final volume. V final to the 2/3. We can get that isolated on one side if we divide by T final. So I'll have T initial over T final times V initial to the 2/3. And I haven't solved for V final yet because there's this power of 2/3. So we need to get rid of it. We need to get rid of that power of 2/3. And the way we're going to do that is we're going to raise both sides to the 3/2 power. So remember how this works. If I have something to the 2/3 power, which then I raise to the 3/2 power, what you effectively are doing is you're multiplying the powers. And 2/3 times 3/2 is just 1. And so on the other side of the equation, we'll have T initial over T final, 3/2 power. And then V initial, it's the same deal. We'll take 2/3 power times 3/2 power and just get 1. So therefore, V final is what? Well, what we're told is that the temperature has doubled. So what that means is the ratio of T initial to T final is 1 divided by 2. So because T final is twice T initial. So the ratio is 1 divided by 2. We'll take the 3/2 power, and then we'll have V initial next to that. And if you calculate that 1/2 to the 3/2 power, you get 0.354 times V initial. So that's what we were looking for. How does the final volume relate to the initial volume? We can get it using the adiabatic relationships. Okay, so for that last example, we used the relationship T times V to the gamma minus 1 is constant, and we found that V final is 0.354 times V initial. Okay, so let's do a little bit more with these adiabatic relationships. Here's a question that I'd like you to try to work out on your own. So after I read this to you, please pause the video and see if you can get the answer. Here we have 1.05 mole of air, which primarily consists of O2 and N2 molecules. So that's by far what is most common in the air is O2 and N2 molecules, which are both diatomic. Okay, so this air is held inside of a cylinder. The air initially has an absolute pressure of 3.5 atmospheres and a volume of 9 liters. The air is compressed adiabatically to a final pressure of 5.5 atmospheres. What is the final volume of the air in liters? What is the final temperature of the air in degrees Celsius? So we have a number of constants and unit conversions given. So just take a look at those. You'll use these in your calculations. And then we'll assume that for the air, the vibrational degrees of freedom of the molecules are frozen out, but rotational degrees of freedom are active. So try to work this out, see what you get, and then we'll discuss it. Okay, so in this case, we're dealing with air, which again is primarily O2 and N2. So we can treat it as if the air is just a bunch of diatomic molecules and there's very little else. So what about our degrees of freedom here? Well, we have 3 translational and we have 2 rotational. but we have frozen out the vibrational degrees of freedom. Again, those are only going to be active if the temperature is crazy high, so typically it's going to be frozen out. So we have a total of 5. And so for gamma, which is 1 plus 2 over f, I should say, we have 1 plus 2 over 5, which is 7/5, 7 over 5. Since what we want here is a relationship between pressure and volume to start off, we'll go back to P initial times V initial to the gamma equals P final times V final to the gamma, because what we're going to get is the final volume. That's what we're going to solve for. Okay, so if I want to solve for the final volume, V final to the gamma is equal to P initial divided by P final, so I'm dividing out P final on both sides, times V initial to the gamma. And again, I haven't solved for V final yet because there's a gamma power and I want to get rid of it. So the way this is going to work is if I raise both sides to the 1 over gamma power, okay, I multiply the powers on the left side, and I get gamma over gamma, so that's just 1. And on the other side, I have P initial over P final, 1 over gamma power. And then I have V initial to the first power. So again, gamma times 1 over gamma just gives you 1. Okay, cool. So now we can put some numbers to this. V final, the ratio of the pressures, P initial divided by P final. Well, P initial was 3.5 atmospheres. P final was 5.5. And notice how it doesn't really matter what unit we put in there because it just goes away. And then the power is 1 over gamma. So the inverse of 7 over 5 is 5 over 7. And then we have our initial volume over here. What was that? That was 9 liters. So our final volume after the gas has been compressed is 6.517 liters, or about 6.52 liters. So we'd also like to know what the final temperature is. And there are 2 ways you can do this. You could use another one of those adiabatic relationships if you wanted to, or you could just use the ideal gas law. Either way works just fine. I'll use the ideal gas law for this solution. So PV equals nRT. Temperature is PV divided by nR. What do we know? N is equal to 1.05 moles. We also know that R is equal to 8.314 joules per Kelvin mole. And we know the pressure and the volume in the final state. So therefore, we just need to do a little bit of unit conversion before we can plug the numbers into the ideal gas law and get the final temperature. So here, let me label this a little bit better. So we're finding the final temperature, right? T final. That means I better be plugging in the final pressure and the final volume. And the final volume, or sorry, the final pressure, P final, is 5.5 atmospheres. So let's convert that to pascals. That's 1.013 10 to the 5 pascals in every 1 atmosphere. Cancel out atmospheres. And we get 5.572, keep 3 sig figs, 10 to the 5 pascals. And I just want to remind you that 1 pascal is equivalent to 1 joule per cubic meter. So we're going to use that. Okay, what about our final volume? This is the one we just calculated. we found it was 6.517 liters. And we want to get this in cubic meters to have all the units be SI units. So 1 cubic meter is equivalent to 1,000 liters. So what we have for our final volume is 6.517 10 to the minus 3 cubic meters, because of course the liters cancel out in that unit conversion. So T final is, we're going to plug in using this expression. P final is 5.572 10 to the 5 joules per cubic meter. The final volume is 6.517 10 to the minus 3 cubic meters. And then we divide that by N, which is 1.05 mole, times R, ideal gas constant, which is 8.314 joules per Kelvin mole. So let's see how the units work out. Meters cubed will cancel, joules will cancel, and then mole also going to cancel. And then Kelvin goes back to the top, so we're getting a temperature in Kelvin. We have 415.97 if you do the calculation, but we'd want to round that to about 416 Kelvin. And if we wanted to put this in degrees Celsius, remember how this would work. We would take 416, subtract 273, and we would get about 143 degrees Celsius. Okay? Okay, so we now have some adiabatic relationships, again, that we can use to relate pressure, volume, and temperature during an adiabatic process. And we can use that to plot out on a PV diagram what an adiabatic process would look like. So if we start at some initial state, some initial pressure, some initial volume on the PV diagram, and we work our way to some final state, we know the curve that takes us between those 2 points. It looks something like this. And the defining feature of this curve is that P times V to the gamma is constant along the curve. Okay, so that's how we plot this out. So what we want to do next is something that we did for the other types of processes we looked at, which is to look at the first law of thermodynamics as it applies to an ideal gas. We have Q is equal to W plus delta E internal. We're going to look at each one of those three terms, come up with a formula for it, again, just like we did for the other ideal gas processes. So let's do that now. Okay. So for an adiabatic process, it's really easy to say what Q, the heat transferred to the gas, is. It's 0. That's just by definition. That's what it means to have an adiabatic process. So if we then apply the first law, we can see that Q is equal to W plus delta E internal. But again, there's no heat flow, so 0 is Q. That's equal to W plus delta E internal, which means delta E internal is equal to minus W. So in other words, the internal energy change of a gas during an adiabatic process is the negative of the work done by the gas. Okay, so Q, delta E internal, we know how to handle both of those. All we need to do now is calculate what the work would be for an adiabatic process. And the way we calculate work is we integrate P dV. Okay, so we have to be a little bit careful about how we carry out this integral. One fact that we're going to bring into play is our adiabatic relationship. PV to the gamma is constant during this process. Okay, so let's call that constant, how about we call it K? So what we have is pressure is K divided by V to the gamma. Or we could also say the pressure is K times V to the minus gamma. Okay, so therefore, in our integral, we're integrating from an initial volume to some final volume. The pressure we're going to write as K times V to the minus gamma. And then we have dV. So that tells you what sort of integral we're doing. Okay, so this is just an example of the power rule. Because we have V taken to some power, K is just a constant. So here's what we have to do. K is a constant. If we have the power rule and we're integrating, the idea is we started with a power of minus gamma, but we add 1 to that. That's how we integrate a power rule. And then we have to divide out front by that same power, so minus gamma plus 1. That's how we integrate the function in the integral. And again, we're going to evaluate at the limits V initial to V final. So what we have then is I've got 1 divided by 1 minus gamma. And then when I plug in the top limit, I'll have a factor of K, and I'll have V final, because that's the top limit, to the 1 minus gamma. And then I plug in the bottom limit, so subtract K times V initial to the 1 minus gamma. Okay, the next thing I'm going to do is a little bit of a substitution trick. Remember what this thing K was in the first place? K is equal to P times V to the gamma power. And it's constant, so in other words, we can pick any point along the curve, and P times V to the gamma power is going to have the same value. So I could say K is P initial times V initial to the gamma. That will work. Or I could say it's P final, V final to the gamma power. Again, that will work too. Those are the same thing. Okay. So we're going to make that substitution for K. I have 1 divided by 1 minus gamma. So the first time I see the constant K, I'm going to sub in this. So P final, V final to the gamma, multiplied by V final to the 1 minus gamma. So in other words, I plugged in K right there. Okay, for the other one, I'm going to plug in this for K. That's the initial values. So I have P initial, V initial to the gamma. That's where K goes. And then I have V initial, 1 minus gamma. All right, so actually that simplifies quite a bit. Because if you take V final to the gamma power, and then you multiply by V final to the 1 minus gamma power, you can combine those by adding the powers. So what's gamma plus 1 minus gamma? Well, it's 1. In other words, this is the same as saying P final times V final to the first power. And then by the same token, we have P initial times V initial as the second term. And then again, we have 1 divided by 1 minus gamma out front. Now we could end the story right here, but I just want to remind you what gamma is. Gamma is 1 plus 2 over F. In other words, gamma is always going to be something greater than 1, right? Because F is never going to be negative. Gamma is always going to be something greater than 1. And what we're doing in the expression is we're doing 1 minus gamma. So if gamma is greater than 1, and we're doing 1 minus gamma, that's going to be something negative. Okay, so I don't want a negative sign kind of hiding in our equation, so here's what I'm going to do. I'm going to write minus out front, and then I can switch this to gamma minus 1. Okay? And then I'll have P final, V final, minus P initial, V initial. And then to end this off, if I put the negative sign into the brackets, that would be the same as switching the order of the two terms. So what we have is P initial, V initial minus P final, V final divided by gamma minus 1. That's the work. Again, internal energy change is just negative work, which again we just found the expression for, and Q is equal to 0. So these are all the different things we might want to know about an adiabatic process in terms of the energy. Okay, so if we take the results we just derived for Q, W, delta E internal, these are the results. Again, Q is 0 by definition. The work we can express as P initial, V initial minus P final, V final over gamma minus 1. And then the internal energy change, delta E internal, is minus W. So an adiabatic process is defined by no heat being exchanged between the gas and the environment, which means if the gas is going to do work, let's say the gas is going to expand, okay? It's going to have to do that by giving up some of its own internal energy, okay? So that's how you want to think about this. Any work done by the gas has to come at the expense of its own internal energy because there's no energy flowing from the outside. There's no Q. Okay. In order to actually make any of these calculations, we need to know gamma, and therefore we need to know F, the degrees of freedom. So unlike those other processes, for an adiabatic process, it matters what type of gas molecule we're dealing with and the number of degrees of freedom it has. Okay, so I have a question. It's a conceptual one for you guys to work out, okay? So we're going to consider two different processes which start at the same point on a PV diagram. So that initial starting point is going to be right here, where we have V initial for the initial volume and P initial for the initial pressure. In one case, the gas is going to expand adiabatically to this final volume right here, okay? And the final volume is bigger than the initial, so that's what we mean by the gas is expanding. In the other case, the gas is going to expand isothermally to the same volume. So imagine an adiabatic process where we go from here to the final volume, and then an isothermal process where we go from here to that same final volume. Which statement about the work done by the gas is true? So is there more work done for the isothermal case? Is there more work done for the adiabatic case? Or is the work going to be the same for each case? Try to work this out. See if you can come up with an answer, and then come back to the video, and then we'll go through it. Okay, so we're comparing two different processes. One is adiabatic. And by the way, we know that for an adiabatic process, PV to the gamma is constant. So we're going to actually use that to think about what's going on here. One way we can write this is P is proportional to V to the minus gamma. And then also remember, gamma is 1 plus 2 over F. F is just counting degrees of freedom. That's always going to be positive. So gamma is bigger than 1, okay? In other words, pressure goes as V to the minus gamma, where gamma is some number greater than 1. That's adiabatic. For isothermal, we have PV, let's just write the ideal gas law. PV equals nRT. Isothermal means constant temperature. That's the meaning of isothermal. And the number of gas molecules and R are both constants too. So what we say is PV is constant for an isothermal process. That's kind of the defining feature. Okay, so therefore we can say, for isothermal, P is proportional to V to the minus 1 power. Because if P times V is constant, we can divide out V, and pressure is some constant divided by V, which is like saying it goes V to the minus 1. Okay. The point of all of that is to say the adiabatic curve on the PV diagram. It falls off faster. It's steeper, in other words, because the isothermal curve is v to the minus 1, and the adiabatic curve is v to the minus some power that's bigger than 1. That means it falls off faster. If we plot it out, okay, PV diagram, and again, we start at the same point. We're up here somewhere. Here's V initial, and we'll expand the gas to this V final over here. If I start by drawing the adiabatic curve, let's say that's the adiabatic curve, label it number 1. I know the isothermal curve doesn't fall off quite as fast, so it's maybe up here somewhere. Okay, that's what we figured out by just looking at the powers. Okay, well, we're comparing work. So clearly they don't involve the same amount of work. I hope that's clear from just looking at this. So work is integral PdV, which is, again, the area under these curves in the PV diagram. Well, clearly curve number 2 has more area under it because it doesn't fall off as fast. So compared to curve number 1, there's more work. And what we say is number 2 was the isothermal one, so more work in the isothermal process compared to the adiabatic. In a nutshell, you get more work out of an isothermal expansion compared to an adiabatic expansion. That's what this says. Okay, so here's a follow-up to that question. It's a similar scenario. We have two different processes that start at the same point on the PV diagram. So we start over here now. This will be our V initial, P initial state. In one case, we're going to contract the gas adiabatically. So we're moving this way towards smaller volume. Okay, we're moving to the left. In the other case, we contract isothermally, but we end up at the same final volume. Okay, so just think we're contracting the gas as opposed to expanding the gas in this case. So what's true? Is there more work done in the isothermal case? Is there more work done in the adiabatic case, or is it equal? By the way, one quick note, since we're contracting, the volume is decreasing, the work is going to come out negative. But what I want you to do is, don't worry about the negative sign, I just want you to compare absolute values, okay? So try to work this out, and then we'll go through it together. Okay, so to work this one out, we're going to remember that the adiabatic curve, and we'll label that number 1, is steeper than the isothermal curve, which we'll label number 2. Okay, so all we have to do is then draw the curves on the PV diagram. And the important thing to remember is that we start the two curves at the same initial state over here. So this would be V initial. And they're going to end up at the same volume. But they're not going to end up at the same pressure because the curves don't have the same steepness. Okay, so let's draw curve number 1. Something like this. And let's draw curve number 2. That's the isothermal. Again, it's less steep, so we'll draw it like this. So there's 1 and 2. So you might have guessed that this question has the same answer as the previous one, but it actually doesn't, because here, when we think about work as area under the curve, curve number 1 clearly has more area, if we, again, just think about absolute values, and more area than number 2. which says in this case that there's more work involved in the adiabatic process than in the isothermal. So what that's saying is if you're going to compress a gas, it's going to require more work to do it adiabatically than if you were to do it isothermally. Okay, so let's do an example where we actually calculate work for an adiabatic process. Okay, so in this case, we have a monatomic ideal gas that contracts adiabatically. So we start here, and then we move to a smaller volume, and the pressure is going up as we do that until we reach this final state. So calculate the work done by the gas during this process, and we'll do it by work is equal to the integral of P dV. So let's see what we get. All right, now, so what we're going to do is calculate work using the integral P dV, but we already worked this out. We already derived what this is for an adiabatic process. We have P initial, V initial, minus P final, V final, over gamma minus 1. Okay, so this is how you calculate work for an adiabatic process. Okay, so we already worked that out. But what we need to know is gamma. And remember, gamma is 1 plus 2 over F. Well, actually, what we have in the formula is gamma minus 1. So if we were to solve for that, it would just be 2 over F. And F is equal to 3 because we have a monatomic gas. So therefore, gamma minus 1 is 2 over F is 2 over 3. Okay, so now we can directly calculate work. So just take note of the fact that we have 1 divided by gamma minus 1. So if gamma minus 1 is 2/3, 1 divided by gamma minus 1 is 3/2. 3/2. And so that's multiplying P initial times V initial minus P final times V final. Well, the initial pressure, that's when we're in the initial state over here, read it straight off the graph, is 1 atmosphere. The initial volume is 4.6 liters. Then we'll subtract P final, which read it off the graph is 4 atmospheres, times, P final is 4 atmospheres, and V final is 2 liters. Again, read that straight off the graph, 2 liters. So that's the calculation we need to do. Units come out as atmospheres times liters. And if you crunch these numbers, you're going to get minus 5.1. So minus 5.1 atmosphere liters. There's a unit conversion we can do to get that into units of joules. And every 1 atmosphere liter, if you remember, is 101.33 joules. Cancel out atmosphere liters, and you're going to get minus 520. So the negative sign, by the way, indicates that the gas is contracting. Whenever the gas contracts, the volume is decreasing, you have negative work. Whenever gas expands, you have the gas doing positive work. So here's the meaning behind that, okay? So W, let's just clearly state that this is the work the gas does on its environment. That's what W means. So if W comes out positive, that means the gas is doing some work on its environment. It's pushing it out. So imagine blowing up a balloon or something like that. The gas is pushing outwards. It's doing positive work on its environment. On the other hand, if you wanted to contract a gas, it would have to go the other way. The environment would have to be doing work on the gas to push it inwards and shrink it to a smaller volume. which is indicated by this negative sign. That's what it means. And so those are the answers. The work is minus 5.1 atmosphere liters, which is equivalent to minus 520 joules. Okay, so we're basically at the end of the lecture here. So we've covered everything we wanted to cover in chapter 19. So I'm going to end by summarizing, because we derived a lot of different equations. There's a lot to keep track of. So real quick, I'm going to summarize everything just so you can see it in one place. So first of all, a really important part of the chapter is ideal gas processes. And in particular, we have 4 that we really need to know well. We have isochoric, which is a constant volume process. You have isobaric, constant pressure. Isothermal, that's constant temperature. And then finally, we just learned about adiabatic, which is zero heat transfer. So we need to know all 4 of these very well. And we know how to plot each one of them out on a PV diagram. So isochoric, that's what's labeled as A. Again, if the volume is not changing, that's going to look like a vertical line on the PV diagram where you stay at one constant volume. Isobaric, constant pressure, that's going to look like a horizontal line where the volume can change, but you stay at the same constant pressure the whole time. For isothermal, we know it looks like this. We have an isothermal curve, but it's not quite as steep as the adiabatic curve, which falls off much more steeply like this. By the way, one thing that you may see on PV diagrams in the future are things called isotherms, isotherm curves. So what you see, these dashed lines labeled 1, 2, and 3, these are different isothermal curves, so they all have constant temperature, but the temperature for each one is different. So T1 is a smaller temperature if you're following this curve, then T2 if you're following this curve, then T3 if you're following that curve. Okay, so that's something you may see on diagrams from time to time. It's just like different constant temperature curves. We call those isotherms. All right. So I'm not even going to attempt to read all of this out for you, but let me just tell you what's in the table. We have different processes. We have isochoric, isobaric, isothermal, and adiabatic. For each one of these, I tell you what the defining feature is. So for example, isochoric means no volume change, delta V is 0. Then we also look at Q, heat transfer, delta E internal, and work. So in other words, for all of these different things, Q, delta E internal, and W, we've derived formulas for each one, for each of the processes, expressed purely in terms of pressure and volume. So that way, you can use these formulas, and if you are just looking at a PV diagram, right, all you know is volume and pressure information, you can use these formulas to calculate it. So all of these formulas have been derived. We saw the derivation for them at some point in the lecture, so I'm not going to go through that again. But at the bottom of the slide, I want to point a few things out. CV is what we call our molar specific heat for a constant volume process, and that appears various times in our formulas. Well, the formula for CV is F over 2 times R. So that's important to remember. CP, again, this is going to pop up in a lot of different formulas when you calculate heat and work and things like this. That's just CV plus R, so important to remember that. And then finally, gamma, which pops up in the adiabatic relationships, it's defined as CP divided by CV. Oops. And so these are just all the different things we derived. There's a lot of it. So, as usual, we have practice problems at the end of every lecture. We're not going to have time to get into any of these practice problems in today's video, but the answers to all of these practice problems are given in my notes, okay? So you'll see these in my handwritten notes on Canvas if you're interested in looking at the solutions to any of these practice problems. And again, you're not required to do these. These are just to help you study. So especially as we approach the first test, you're going to want to go through some of these problems to help you study. So with that said, that's it for this lecture, and that's it for chapter 19. So I'll see you in the next video. Until then, take care.